Welcome back. Today we're going to be finishing up chapter 3 and looking at inverse functions, which are going to be the functions in reverse. So we're going to be looking at what happens as we take a function and we go backwards and we switch the input and the output and we see, can we get from the output back to the input? So without further ado, let's get started on section 3.7, inverse functions. All right, so a function that is one-to-one has an inverse. This is why when we started talking about functions at the beginning and we learned how to identify one-to-one functions with the horizontal line test and with what we'll learn today about checking for inverses, it's really important to know that one-to-one functions and inverses go hand in hand. If a function does not or is not one-to-one, then it's not invertible and we don't have a way to find the inverse unless we restrict the domain by adding some words to say, hey, but we need to restrict the domain from 0 to infinity, or so on. So in a machine diagram, which I'd really like to just look at, even though it doesn't teach you any math, it shows you what's happening. We take a domain, or we take an x, and usually we funnel it through a function, and we receive a range, or a set of y values. In an inverse function, or f inverse of x, we take the same y values, we funnel them back through the system, and we receive our domain, our original domain. So before we even get started, one of my favorite ways to think about this is with giving tests out in class. So let's say I give out a bunch of tests in class, and I say, Jimmy, you get 100, and John, you get 100. That's totally allowed in a testing situation, right? But then, let's say they hand the test back without names, and I have 200s, and I'm looking at them, and I don't know whose test is whose to give it back, right? But an invertible function, for the most part, unless you have a very common last name, would be first name, last name. So now let's say we do the same thing, but with first names and last names. And I say, okay, if everybody has a different last name, and everybody has a different first name, and I say, John, your last name's Smith, and Jimmy, your last name's Martin, and I say, okay, if your name's John, you get this Smith. And if your name's Jimmy, you get this Martin. Then we can go backwards and I can look and say, oh, I've got two tests and one says Martin and one says Smith. Well, I can give them back to Jimmy and John knowing who they are. So when you have exactly one input corresponding with exactly one output, you definitely have an invertible function. But when you don't have that, and when you have 4 people in a class that make 100, you can't go backwards. You can only go forwards. And so it's really important as we get started and as we get rolling through this for our brains to think, wait, in the first place, is it invertible? And then in the second place, which is what we're going to find today, is what's the inverse. All right, let's get started with the simplest form of this at all, which is they just give you an inverted function, and they said, what was the corresponding regular function? Well, that means that this was even though this is an x being input to an inverse, right? This is an input, and 2 is an output. The original function was probably h, and when we just said an inverse is just switching the inputs and the outputs, the original function was h of 2 equals 6, because we took the x and we took the y and we switched them. And that's how we invert. The simplest invert is when we just have a function, one input and one output. Now, the test for an inverse is a little more tricky, but it's not too bad. We're going to use the skills we learned in the composite function section, and we are going to test and see if both the composites give us the same thing, and if that thing is x. And so we're going to have to do some practice composing functions or finding composite functions, but if they yield the exact same result and that result is x, then we've got a set of inverse functions. So first thing we're going to do is we're going to look for f of g of x. We're going to say, okay, well, g's on the inside and f is on the outside. So that what this one is, we'll make this one red. This is plugging g into the x values of x. And so we'll put parentheses where the x was and we'll rewrite the g. So the cube root of x plus 4 minus 4. And then we'll solve it down. Oh, cubed. I missed that cube right there. And when we solve it down, the cube and the cube root cancel. And we're left with x plus 4 minus 4. Because boop, boop. And then we see the 4 and the 4 cancel, and we're left with x. So we've got one condition where it looks like these are probably inverses. But we have to check the other side to make sure it's true. So we're going to go to the other side, and we're going to check the exact same type of thing, but with a different inside-outside function. So in the previous one, g was on the inside. Now f is going to be on the inside. And so our x3 minus 4 is on the inside, and we're plugging that into the x value of g. So we get the cube root, and we get plus 4. When we work this out, we're going to see those 4's kind of go away again, which is really nice. And we're left with the cube root of 3, and we've got x by itself, which means not only are these the same, but it's x, so these are inverses of one another. All right, the next one's very, very similar, so we're going to skip it and let you work on your own. Try it on your own. See if you can practice finding out if functions are inverses of one another. A small side note on domains and ranges is if x and y are getting switched in this inverse function situation, then it would only make sense that the domain of the original function becomes the range, and the range becomes the domain. And so this problem, this triad, is not too crazy, because they give us a domain, they give us an original domain, and we'll go f of x. The original domain of f of x was 1 to infinity, and the original range was negative infinity to 2. And what we're going to do is we're going to invert that thing. So the inverse, the new domain, is going to be negative infinity to negative 2, and the new range is going to be 1 to infinity. All we did was switch them. Not too bad. So now let's look at it on a table, and we'll look at it how it would work, and very similarly on a graph. All right, so the first thing is just review. F of 60. Can you find where the input of 60 turns into the output? F of 60 turns into 50. Done. That's function notation. That comes from the very, very beginning of this chapter. But now we got to go backwards. I'm going to say, well, where does f turn into 60? Another way to think about this would be f of, and this is not f inverse, this is f of blank equals 60. And that would be a cooler way to write the inverse, where you can see it happening in the original function as well. And so where does f equal 60? Right there, and we're going backwards, so we're left with 70. Cool. The graph is really, really similar. We're going to look at the exact same thing, and we're going to say, where does g give us 1? Or g of blank equals 1. It's going to occur at that red line. We're going to see that g of 3 equals 1. Because that point 3, 1 is your x comma y. So that means when you switch them, you'll get the other point on your inverse function. And similarly, we can do the same thing up here at 4. Ooh, and that's not a perfect number, but let's just, I don't know, let's say it's 5.5, and if it's not, that'll be on me for picking a bad problem. Because when you drop it straight down, it looks like you get about 5.5. All right, now here's the meat of this section, is finding the inverse, is applying these 4 steps to finding the inverse. And I'm going to go step by step with the book because I think it's really important to catch these steps. Step 1, make sure it's 1 to 1. So before you can even do anything, you got to say, is it 1 to 1? Does every single x value have a unique exact y value? And in order to do that, the most common and easiest way to look at that is to ask yourself, what type of function is it? We know that this function, because the exponent is 1, is a linear function. And does a linear function pass the horizontal line test? Let's see. It does. So because it passes the horizontal line test, because it's a linear function, we know it's 1 to 1. Step 1, good. Step 2, solve for x. So in this one, usually we're getting y by itself. We're going to try to get x by itself. So right now we've got y equals 1/3 x minus 5. Maybe we'll move that 1/3 over and go 3y equals x minus 5. Maybe we'll even move that minus 5 over, and we'll get x equals 3y plus 5. Solve for x. That's step 2. Step 3, swap x and y, and now we'll get back into y equals form. So we're going to swap those two in the green step, y equals 3x plus 5. And then step 4 is really important so that we're not just writing a y equals form, because these are two very similar functions. They're going to look pretty similar. They're both going to be linear, but there's something very specifically different about them, is that they're inverses of one another. So if we were just to write y, I wouldn't know which one you're talking about. Are you talking about the original f of x, or are you talking about the inverse? And so step 4 would be to write it as f inverse of x equals 3x plus 5. And probably for a better notation and for a careful problem, they would have said f of x up here, so you really would know what you are inverting and what variable to use as your function. Now that's the steps to finding an inverse. It does get a little tougher than that, but the steps never change. The algebra might get a little tougher. The steps are never going to change. For try at 8, what we're going to do is we're going to find the inverse of a function and find the domain and the range, which is going to be, there's going to be a little bit of thinking involved in the domain and the range section. And so the first thing I'm going to do is I'm just going to find the inverse of the function in the normal way that we know how. So we've got y equals 2 minus root x. I switched it to y so it's a little easier for us to work with. I'm going to get x by itself by moving the 2 over. So we got y minus 2 equals negative root x. Move that negative over. You get 2 minus y equals root x. Square both sides. You end up with x equals 2 minus y squared. And then to make that a little prettier, let's go ahead and FOIL it out, and we'll end up with y squared minus 4y plus 4. But we're not done because we haven't written it in inverse form yet. We've just solved for it. So we need to switch x and y and write it as that f inverse. So the f invert is equal to x squared minus 4x plus 4. And that's our inverse function. Now we need to find the domains and the ranges of these. We need to be really careful with these because the domains of the functions are going to be dependent upon the ranges, and they're going to be dependent upon it being invertible. So they had to have given us an invertible function, which they did. And if we graph this, we know that this is a vertically flipped, shifted up 2 square root function. So what we know about this already, we can look at the domain and the range from the graph and say, okay, our domain starts at 0, including 0, and goes to infinity. And our range looks like it goes all the way up to that same point. We know it's shifted up 2, so it's going to go all the way from negative infinity to 2, right? And that's nice. So we've got some restrictions that naturally happened in the equation that caused this to pass the horizontal line test, right? You'll notice it kind of looks like a sideways parabola. And if they would have completed that parabola, which would be if they included the positive and the negative side of the square root, it would no longer pass a function test, and it wouldn't even be a function, much less invertible. And so what we're going to do is we're going to take this equation and this domain and this range and use the properties of switching x and y to solve for, or not solve, but to find the other two domains and ranges. And so we've got the domain of f of x to be 0 to infinity, and we've got the range of f of x to be negative infinity to 2. And so we know, if we look at the inverse, f invert of x, those are just going to switch. And our new domain is going to be negative infinity to 2. And our new range is going to be 0 to infinity. And chances are, if you were to look at that function, and you were to start at 0, right? If your range starts at 0, it's going to be right here. And if your domain stops at 2, it's going to look a little bit like that, right? And we're going to go all the way to negative infinity, and we're going to go all the way up to infinity, so it's probably going to look a little like that, which looks just like half a parabola turned right side up this time instead of upside down. So that's kind of a cool thing to look at, especially as we move on into looking at what the graphs of these things look like as they reflect across that line y equals x. And so I think they only asked us for the domains of both. We gave the ranges because we knew if we'd had the domain and the range, we could just flip them. And so we've got our inverse function, the domain, and the range. Last note we're going to say is we're going to look at this. It's a very similar problem to the one we just had, just not shifted. And we say there's this really cool thing that happens on a graph. When you're graphing an inverse function, because y and x are interchangeable, all we're doing is reflecting each point of the graph across the line y equals x. So every single point, so this point 0, 0, gets reflected across y equals x and stays exactly where it is. But this point that was 4, 2, because we said all of the inverse does is flip the x and the y value, ends up here at 2, 4. And we can see it got reflected by the exact same number of squares across that line y equals x, which is pretty cool. So I'm going to leave this one to try it because it's a little challenging. I'm going to leave you to try this one on your own because it's going to really test your toolkit function graphing. It's going to test plotting points. It's going to test a lot of things. So I want you to try this one by yourself, see how it goes. And don't forget to be practicing the exercises, be practicing all of the past homeworks, watching these videos again if you need to, email your instructor and asking for help on certain problems if you get stuck, talking to students in the class, and finding a way to really master this learning before the next test that's coming up over Chapter 3. Thank you for watching, and I'll see you next time.